Hello, everyone. Welcome back to the lecture stuff on raster geospatial type data and learning some xarray. So I have gone ahead and created a new starter code for you. So you'll have to make sure that you go to Get Kraken in course materials, do a poll, and you should see add starter code for xarray, and that should then be in your workspace. Once you have that, you can switch back over to your VS Code and go into your course materials repo, and then all the way under starter codes, you can go ahead and open up 7 Intro to xarray. And once you do that, you'll see the code that I've got set up for you here. And so I'm going to go ahead and hide the editor there, and I'm going to get this started up in our interactive window. And so this is going to go ahead and give you an error that say failed and say no module named xarray. So as always, we have to go ahead and install this one. So I've given you the install command right here. Go ahead, you can copy that and paste it down into the little prompt down in the lower right. And so I'm just going to go ahead and do that. For some reason that didn't quite go through. So anyways, conda install -cconda forge, and then all of this stuff. And so I'm just going to get this going real quick, and you should see it start to figure out its installation process once you run this. And so basically what we're doing here is installing xarray, of course, and we are doing that from the conda forge channel to keep everything consistent with what we had done for GeoPandas. And then I'm adding a few extra things in here. These aren't strictly necessary for this set of code that we're working with, but will be necessary for the second part of your homework around this, where we will be working with some cloud data sets. That is like cloud computing rather than cloud and weather. But so basically, just to give you a quick overview of what these all are, Dask is for like parallel processing. Xar is that other data format that I talked about in the previous part of the lecture. FSpec is for handling like files over the internet, and then these other ones, AIO, HTTP, and requests are have some nice stuff around pulling data from the internet. So once this is done, you should have a full setup. So in my case here, this has been taking a few minutes, and this one, luckily for us, unlike GeoPandas, should just go straight through, no problems, and you should see it kind of get through here. And I was going to pause the video while this completed, but this looks like it's just going to finish up right here. So I'm going to let that go ahead. Okay, so then eventually you'll get to a thing. Note, you need to restart the kernel to use the updated packages. Let me just make sure. I'm just doing that just so I can get a green check mark here and make sure that this actually did finish up here. So I'm going to clear that, and as always, restart. And that will pop us into a brand new session with all of our new stuff installed. Okay, so with that, we can run our import cell and get everything we need. In this case, we always import xarray as XR. That's sort of the community standard, saves you some typing. And we're going to go ahead and start looking at some data. For this walkthrough, we're going to use just tutorial data, but there will be other data that you'll use in your assignments. You can actually see here, make this full screen. And so you can see here, there's in the xarray documentation from that link I just showed, there's this xarray tutorial open data set. And we're just going to use the air temperature one, but there's all of these other ones that are possible. So feel free to play around. If you want to see some Arctic stuff, check out RASM. If you want stuff about sea surface temperatures, you might check out this ERSST v5 one. So feel free to play with those at your own pace. But with that, we're just going to open up this data set and look at what's in it. So, oh, I guess I forgot to install Pooch. So for me, it's saying I need Pooch, so I'll try conda install there, conda forge Pooch. Never seen that one before. Go ahead and pause this. Okay, I have now installed Pooch, which I guess I had forgotten from here, but I've added it to the conda install up top, so this should work out for you. And I'll put a little note here. Okay, so that has been documented for you. And so you should be able to run that whole command and that should just work for you. I had no issues and hopefully you won't either. Okay. So there we go. Now I did this cell here, XR tutorial open data set and the air temperature one. And then I'm just outputting what happens and I'm assigning it DS, which is kind of a common thing when you just have a generic data set that you're working with in Xarrays DS. So what you see is the sort of the same thing that if you were around in class the other day, you would have seen this in the official Xarray tutorial. And so it shows us each of these things. We've got these dimensions, which are the names of the axes along with their shapes. And then we've got the coordinates, which are the labels along each of those dimensions. And then finally, our data variable is there's just one of them, and it is the air temperature at some height, more or less. So I'm going to go ahead and kind of walk through each of these pieces. But in the meantime, if you want, you can always kind of explore this. This is a really nice way of seeing everything that's in the data. So you can explore all of the attributes and kind of do it in an interactive way. So I'm going to close that up a little bit so it's out of our way and talk about dimensions. So here we go. Our data set has 3 dimensions. There's latitude, longitude, and time. And you can actually look at dimensions with ds.dims, and you'll see basically this is not so different from what you see up here. It's just a dictionary, which you can tell by these curly braces and the colon syntax here. It's just a dictionary, and basically it maps between the label or the name of the dimension and to the shape along that dimension of any variables that have it attached to it. So these are the same as the ones up here, and they are also how we describe a particular point in this variable, which we'll get to in a moment. So just like any other dictionary, you can go back over here. You can actually index or select out on any of those values. So here, if I want to just say the latitude, I can just pull that out, ds.dims, and then grab out latitude, and it gives me 25, just like it does here. You know, you could make this time as well. You know, you can do this for, you can do this for any of the dimensions. So always feel free to play around there. So I'll just switch that back. And so there you go. Time is, there's about 3,000 of those. So just like dimensions is called dims, coordinates is called chords. So just a shorthand, make you type less, but you can pull that out directly too. And this looks a little bit differently, but basically it's telling you, you know, latitudes have are a coordinate and they follow the dimension lat. So in this case, the latitude or the coordinate and the dimensions have the same names. There are cases like for the RASM one dataset tutorial, they aren't exactly the same, but for the most part, you'll see that they end up being that way. And that's something to do with the coordinate representation systems. So in our case, you can see that they are just floating point numbers, right? That is like decimal numbers, and they have these values along each of the dimensions. So, and then time has actual, instead of being floating point numbers, they're actual date times with actual human readable date stamps. So the last one is 2014, December 31st at 18 o'clock, so 6 p.m. So we can see all of the coordinates, and you can pull them out. Actually, so in X-ray, coordinates get kind of a nicer, sort of like a higher level treatment. So you can pull them out of the overall data set, and you'll see that pulls out the time and gives us this interactive version of it again. So you can go ahead and see what's in there. You can see any attributes it has, but you can also pull out, if you want to be very specific and say, I know I'm working with a coordinate, you can do the same thing, and it ends up being exactly the same. Okay, so next up is our data variables. So let me just go back to the original DS so I can point out what we've all been through. So we have looked at our dimensions already, right here. We just looked at the coordinates, and you got to see how they're kind of a mapping between a dimension or some dimensions and then a label, which is just its own array. Finally, we have our data variable. So in this case, there's only one. So we can pull that out. And just as before with everything else, you get this kind of same unified interface where you can look at everything. So it's saying that this is a data array, its name is air, it has these dimensions, it's got some values which are currently not accessible to you, but we'll be looking at them in a little bit. And then it's got the coordinates attached and some attributes. And so these attributes are really things that are kind of for proving where the data set came from, keeping track of things that might have produced it or altered it, and making it generally easier for you to understand. So in this case, it has like units are degrees Kelvin, and the variable description is air temperature. And you can see that this came from something called the NMC reanalysis data set. It's not important what that is, but you can see where everything came from. And if you want to actually access those attributes for any variable or for the overall data set, you can just do .adders. So like everything else in X-ray, they like to keep it concise. So there you go. If you print it out, this is just a dictionary with mapping between, in this case, the key is this long name, which is the same as long name up here. And again, this is the same 4x daily air temperature at sigma level, blah, 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 is the same there. So this is really up top here, just a prettier representation of the underlying dictionary. And so if you want to add things or modify it, you can. You can also, just going back over to the left side here, you can also look at the attributes for the entire data set, which is its own thing, and you can see where it came from. And if you wanted to, you could go ahead and explore where it came from. So I'm going to change that back and make sure we save that, so that way nothing gets changed. So the data set that we were working with, this DS, only has a single data variable, but a data set can contain multiple data variables. And so for this, we can add one. I'm going to add one new one called pressure, which is using the old function that we came up with in some of the first weeks of class, calculating the air pressure at some height and temperature. So I just copied and pasted this over here, but it's a function that has a name, air pressure at height and temp, and it takes two arguments, a height and a temperature. Now we have temperatures in DS, so we can actually go ahead and use this. So I'm going to basically say air pressure at height and temp. I'm just going to pick some arbitrary height, 2 meters, let's say. And then I'm going to input the air temperature from the data set, and that's going to come out, and I'm going to label that as pressure. Now, how this actually works is basically under the hood, X-ray does everything that NumPy can do. It just keeps everything nice and orderly here. So this function just straight up works, and it will calculate the air pressure at the height and temperature for every single value of air. That is the whole, every 25 latitude points, every 2,920 time points, and every 53 longitude points. And then it will output that, and we will create that in the data set as a new variable called pressure. And then I'm just, for the sake of being tidy and taking good care of my data set, I'm going to add the units here, are pascals, and I'm going to add the long name, which is going to be standard air pressure at 2 meters. So I'm going to go ahead and do that, and that calculates rather quickly, which is quite nice. But you'll see here we have now our pressure, and it's got the same dimensions, time, lat, and lon. And I can go ahead and open up the attributes, which is this little paper icon. And that says the units are pascals, and the long name is standard air pressure at 2 meters. So this is how you can start to kind of create your own data sets and do computation on stuff. But it's as far as things go, just keeping track of units and coordinates and things like that is nice, but it would be nice to be able to do more computation, do things like pandas. So this is where we kind of get into how we actually do computations and stuff. And before I do that, I do want to show you that like underlying the data set here is basically just NumPy arrays. So if I do ds of air and then do a dot values on it, that actually pulls out the underlying NumPy array and gives it back. And so I prove that here by printing its type, and you can see that it is just a NumPy ND array. And I can also look at, for instance, the shape of the array, and that has the same shape as we had in the dimensions. So it has time, then lat, then lon, and you can do that mapping, like here, and then 25 latitude. So you can see that under the hood, it's just a NumPy array, but we basically have all of this other stuff alongside of it. Okay, so back to xarray stuff. There's kind of 2 ways of generally selecting out data. There are other ways to do fancier things as well, but the ones that you probably will end up using the most are .icell for index select, which has indexing kind of like NumPy, where you start at 0 and then the next thing is 1 and then 2 and then up until the end of the number of items you have. On the contrary, there's also a .cell. So note icell is index select, SEL is just select, and that's using the actual coordinate labels to select data. So kind of just to show you the icell first, if I want the very first value, I just say I want time of 0, .icell, time equals 0, and that gives me that first time. And we can go ahead and see 2013-0101, and that was also the first time right here. But also when you select it out, it automatically, because there are no other time values, time is no longer a dimension, because these data variables no longer vary with time. Okay, but you could also, if you knew, for instance, that this was the first time, which we do now by looking at it, you can also do .cell and have your human readable time here. And you can check that the first time using .sel and using .icell are the same. So I did the equals here, and then you can see that this turns it into a Boolean array, and we have all true values. So these 2 things are equivalent. It's really just a question of what you want to do. So, just as well, I could do ds.cell and then time equals. Now, if I wanted to say, let's look at, I don't know, 2013, let's look at October 1st, and go ahead and do that. So then if I pull this out, I just grabbed, that was the time I wanted. And now it will actually say to me, there are actually 4 times that match that query. because this is every 6 hours is this data. So you'll see there are my 4 times. So there's basically at midnight, there's at 6 a.m., there's at noon, and then there's at 6 p.m. or 1800 in the way that this is written. So you can just go ahead and kind of query things like that, and it will give you out basically what you are looking for. You know, just as well, I could do ds time equals 2013 dash. Well, I can just look at 2013, and then it will get me 1460 times. So this is a way that you can kind of more easily grab out times that correspond to real events or something like that. Okay. But moving on, we can also select out multiple coordinates rather than just one at a time. Now I'm going to grab out, as I did in class the other day, the Tucson latitude and longitude, and then I'm going to put that into a .sel and then say I want the latitude and longitude. Now I'm also saying method equals nearest here because the exact latitude and longitude are not, these exact values are not in here. So I'm just saying, give me the one that's closest. And so you'll see I grab that out. Latitude and longitude, this is the closest for these two. Okay, and so from here, I can, I'm noticing that this is 200 is the closest longitude. What do okay, just curious about where we're looking at. I think I had the wrong idea. Okay, so from here we can see that it pulled those out, and then we just keep the time dimension. So now I have all of the times. So now if I wanted to see that, so apparently this is not at all close to where Tucson actually is, but we're going to go with it. And so you can see here, we can just call dot plot, and it will nicely give us all of our data and put it on a time series plot. You can do the same thing for the pressure, and you'll see it's basically the same idea, but what you will note is it changes what puts on these axis labels and limits to be basically what comes out of the attributes. So this is a really nice way to automatically annotate your plots. So doing just dot plot on something that only has time values automatically gives you the time series plot. We could also grab out, here we go with ISL, just grabbing the 30th time step. We can just grab that out and then do dot plot again. Now this data object is going to end up having latitudes and longitudes as dimensions, but no time. So xarray automatically tries to basically grab out and plot things in a way that makes sense. So in this case, a map. So, and now I see why things are as they are. These are degrees east, so we're counting up. Normally, I would have thought it would be the other way around. So if we actually say 360 minus, oh, what have I done? Okay, it's some crazy keyboard shortcut there. Let me try this again. Delete all those. Okay, let's try that again. 360 minus, and now this will give us Tucson. There we go. Lat 250, which puts us right around there. So yeah, if you look at this map and see, this is where doing some data viz can help you correct for some errors. So right around here, if you kind of squint, this is the west coast. You can kind of see Florida and the east coast here, going up into Canada and a little bit of Alaska down through Mexico. So this is basically the North America region. Okay, so now with that, I'm going to rerun these. And there we go. Now this is Tucson. This makes a little bit more sense. Okay, so I can do the pressure again. I'm just going to run through this whole thing. So now, again, where we ended up making a map for a particular time. So this was January 8th at noon of 2013. And this is just the air temperature profile across basically North America. So just like pandas, there's a lot of things that we can do to help in data analysis besides plotting. In this case, we can do things like rollings and group bys. So in this case, if we wanted to look at that Tucson air temperature, and we wanted to look at like a 30-day moving average, we can do that. So I'll plot the original one, and then I'll also take that 30-day rolling average. So every we're taking 30 days, a 30-day window around any point in time, and then calculating its average, and then we'll plot that as smooth. So there we go. You can kind of see now a little bit less noisy, the actual pattern of that temperature through time. And similarly, there is a way that you can do group bys. It's basically the same idea as in Pandas. So I'm going to take Tucson DS, and then it has this DT, which is basically gives you all the options for grouping by time. And one of them happens to be season. So this will be June, July, August, September, October, November, then January or December, January, February, and so on. So I can go ahead and run this, and basically I'm going to pull out that seasonal time group, and then I'm going to say ds of air dot group by season, and I just want the seasonal averages. And then when I print this out, it gives me all the numbers back right away. But basically we get a new X-ray data array where now time is no longer a dimension, but season is. And so now season has its own coordinate, where December, January, February is one of the values, June, July, August, second, March, April, May, and September, October, November. So it's basically gone from 2,900 times to 4 seasons. And X-ray really gives you a lot of ways that you can work with stuff like this really quickly. So just for instance, you can make a thing called a facet plot, where we can easily, one line of code, look at what does that actually look like. And basically what I'm saying here is, in this plot, I want the column, COL, column, to be seasons, and then every 2 seasons or every 2 plots I want to wrap around. So every sort of subplot is a different season in the data set, and then I wrapped it after 2. So just really quickly, I can show it if I don't put the call wrap to maybe make that a little bit clearer. So if I don't add call wrap, it just puts them all together. Similarly, I could have done row is season, and that will plot each of them as rows. And so here you go again. So I just basically made call wrap equals 2 to basically make it a nice square plot that just shows up a little bit more easily. So here you go. As you can see, December, January, February is generally colder than June, July, August. So as expected, but here you can really just immediately see, and it gives you a way to kind of quantify these differences. And you can even see, for instance, in the summer here, the effect of like the mountains, and I guess you can see that in spring as well. But this gives you a really nice way to really quickly make plots that are quite readable and just explore your data. So that is my super fast overview of X-ray. I'm going to stop here, and we will explore more in the homeworks. All right, thanks.